Here we go. Okay. Start in 5, 4, 3, 2, 1. Welcome to class. I hope you enjoyed your break yesterday. Anyway, today we start a completely new part of the course. I talked like this course is about introductory stuff, background information, and then we talk about stars, and then we talk about galaxies. The course is called Stars and Galaxies. So here we've got the course schedule. We're on lecture 17 here, March 25th, right here. The first part were the preliminaries, when we talk about electricity, magnetism, gravity, relativity, things like that. Then we've talked about stars. We talked about our sun. We talked about the birth of stars. We talked about stellar evolution. Then we talked about the death of stars, neutron stars, and black holes. We're starting the last section of the course, which is galaxies. So we're going to be talking a lot about galaxies. In particular, today we're going to talk about our galaxy, the Milky Way galaxy. Then we talk about galaxies in general, and then we talk about the universe, talk about life and everything and forever in 42. Okay. Don't forget that we have a class presentations on April 29th. I expect you to turn in your presentations to me by April 22nd. It can be anywhere from 1 to 5 minutes. You can do it any way you want. You get full credit if you turn in the project. You get extra credit if you turn in a great project. You can work alone or with other people. So the point of and it can be on any topic relating to astronomy as long as it's unique, as long as it's different from everybody else's. And I've sent you a dozen notes about that, so you should have all the linked information. So before we get started, this just came out a couple months ago, and I thought it was interesting based on our talk last lecture.
On January 21st, 2019, for the very first time, NASA's TESS saw a black hole destroy a star. This was a tidal disruption event, which occurs when a star passes too close to a black hole. Extreme gravity causes the star to bulge and break apart into a stream of gas. The tail of the stream escapes into space, but the rest swings around to form an accretion disk. This event, called Assassin 19BT for the All-Sky Automated Survey for Supernovae, which first identified it, happened in the TESS Continuous Viewing Zone. TESS's 4 cameras scan large sectors of the sky, and one constantly monitored this region for a full year. TESS saw Assassin 19BT as soon as it started to brighten, days before other observatories spotted it. NASA's SWIFT satellite quickly observed the outburst in visible light, UV, and, along with the European XMM Newton satellite, X-rays. The UV measurements are the earliest recorded for a tidal disruption to date. They showed the event's temperature dropped almost 50% in just a few days. Such a steep decrease has never been seen in a tidal disruption before. These outbursts are rare, happening only once every 10,000 to 100,000 years in a galaxy like our own. Future discoveries will help us learn even more about these uncommon cosmic blasts.
It's amazing when a black hole eats an entire star. Well, typically what happens is the star is ripped apart, and approximately half of the matter goes into the black hole, and the other half is just ejected into space. And the glowing of that stuff that's ejected is what we observe. Now, today's lecture is all about the Milky Way and the Milky Way galaxy. Many of us don't have the luxury of seeing the Milky Way in North Carolina because the scene is so poor. Those of you that get to the mountains, or especially if you get out west, you can see the Milky Way. The next video is, well, you'll just look. There's really a spectacular view. We tend to talk about the Milky Way as what we see in the night sky here from Earth, and the Milky Way galaxy as the thing that we're embedded in that creates that view. It's just pictures taken from a commercial flight. obviously it's speeded up, but note that you can see the stars slowly rising. You know, I wish we could see the night that clearly in North Carolina. The stars that are moving obviously are other airplanes. So the ancients had theories about stars, and they had theories about the planets and the sun. They really didn't have a good explanation for this Milky Way galaxy. It was just something. So let's talk about the Milky Way galaxy. The Milky Way is known as this, well, for us, it's faint. For people on really dark stars, it's very bright. That just goes across the sky and stays in the same place in the sky. And it's approximately the same brightness regardless of where you're looking, okay? Now, it bulges a little bit in one direction, but for the most part, it's a continuously bright across. We now know that we're embedded in a galaxy, and that's what we're seeing. We're inside it, and so that's what we see. But of course, we had no way of knowing that even as recently as the early 20th century. We believe, and we have very strong evidence, that this is exactly what the Milky Way galaxy looks like. It looks just like the Andromeda galaxy, which is the only galaxy that you can see with the naked eye. It's in the Andromeda constellation. Did look at a star chart and point out to you. I've seen the Andromeda galaxy once with the naked eye. You're seeing light entering your eye that came from the Andromeda galaxy 1 million years ago, before the Homo sapiens existed, with the naked eye. So how did we know that we were in a galaxy? How do we even know what a galaxy was? What's the size and shape of the Milky Way galaxy? How did the Milky Way galaxy form? How do spiral arms of the Milky Way galaxy form? What's the mass of the Milky Way galaxy? And then we finish with the black hole at the center of the Milky Way galaxy. So today is all about the Milky Way galaxy. In future lectures, we'll be generalizing that to other galaxies. How do we even know our position in the Milky Way? So Travis, that's a really good question. And we'll answer it partially in this lecture, but I think the guy at the European satellite, which has measured the distances to about 1 billion stars, really did the best chance of really nailing down our location in the Milky Way galaxy. We'll talk about that in a minute. How do we know we're in a galaxy? Well, everything that you see with the naked eye is in the Milky Way galaxy. But of course, we didn't know that until as recently as up until about 1920s, we didn't know that was the case. The first attempt to do that was in 1785, where he looked around and saw that the number of stars that you could see was approximately the same, regardless of where you looked, in that band, of course, in what we call the Milky Way. And so what he assumed, that we're in this kind of a disk-like thing, and we're at the center of it. Center of it because it's equal brightness everywhere you look, approximately. But the problem was that most of the Milky Way galaxy we cannot see. We cannot see because the view of the farthest reaches of the Milky Way galaxy is blocked by big clouds of dust and gas. These big black clouds block our view. In visible light, in other, like in radio waves and infrared, we can see through to the center of our Milky Way galaxy, but not visibly. And so he was fooled by all of these dark clouds blocking our view. And so he was fooled because he thought we were at the center of this disk of stars, and we're not, okay? So to figure out the size and shape of the Milky Way galaxy and our position in the Milky Way galaxy, we need distances. And to do that, we need bright stars with known distances. We covered this briefly in a previous lecture. What we need is what we call standard candles, stars that we can know, bright stars that we can know their distance. And that's two types of stars. RR Lyrae and Cepheids are stars that oscillate with the frequency that depends on their brightness. So if we can see how fast they're brightening or dimming, what their oscillation frequency is, then we know how bright they really are. If we know how bright they really are, and we know how bright it appears, we use the brightness equals the luminosity over radius squared to calculate the distance. And many of these variable stars are in what's known as globular clusters. Globular clusters, interestingly, for the most part, are not in the galaxy. They're in a halo surrounding the galaxy. And so instead of trying to look through the center of the Milky Way galaxy, which back when all we had were visible light telescopes, you couldn't do, what you can do is look at these globular clusters that we could measure the distance to. And these globular clusters are in this spherical halo surrounding our galaxy, and those we can measure the distance to. And so the first chance that we got to figure out the exact location of the center of the Milky Way galaxy was map all these globular clusters and get the center of all those globular clusters and say, aha, that must be the galactic center. And it turns out that was pretty close. Okay. So globular clusters, again, as we talked about last time, are really, really important. And as we talked about, Cepheids and RR Lyrae stars oscillate, and then when they're in globular clusters, we can measure the distance to them. So here is an edge-on, a face-on view of the best guess of the Milky Way galaxy. The Milky Way galaxy has these series of arms. We've been able to map these. In fact, the Gaia European Space Agency probe has mapped most of the stars within a few thousand light years. So most of the stars around here. And so we actually have very strong evidence for these arms here. Also the fact that all other disk galaxies have arms. Most recently, certainly within my research lifetime, we've discovered that the center of the Milky Way galaxy is not spherical, but has this kind of a bar shaped. It's called a barred spiral galaxy. And then we have named that. And we're in kind of the suburbs, or actually the far suburbs, like the exurbs of the Milky Way galaxy out here. So we lived in a barred spiral galaxy with these various arms. Let me go over, I'll come back to this in various times in this, but let's go to this simulation. Okay, so again, here is the Milky Way galaxy. There's the barred spiral, and note that it is very flat, okay? It is very flat. And we can zoom in. Now, I'm going to show you some things. We'll come back to these later. First of all, let me show you the globular clusters. There. And as you can see, the globular clusters are not in the plane of the Milky Way galaxy, they surround it. And they're all over the place. And the globular clusters are old. They have very, very old stars in them. And so we believe the globular clusters are what's left over from the initial collapse of the Milky Way galaxy into a galaxy. So let's get rid of those. I said get rid of those. Now, I'm not enjoying this. Okay, globular clusters. How do I get rid of them? Okay, remove all deep sky objects. There we go. Okay, so let's go to visibility. The Milky Way galaxy has a disk. It has a stellar halo, galactic bulge. Okay, so the components of this that you will be responsible for is there's the disk that's in blue. The center bulge, this yellow thing, is highlighted there, and then the galactic halo is the red here. Okay, so let's go back. Okay, and there's the sun, the central bulge, the galactic halo, and the disk. It's 80 to 100,000 light years across. This graphic shows 80,000. I don't know what your book says. Most books say 100,000. Huh. You know, what's a few tens of thousands of light years among friends? The disk is thin and flat and consists mostly of gas and dust. And it's the site of star formation. And here's the thing. Anytime you see star formation in any galaxy, it's going to be blue. The reason why is if you have star formation, you're making stars of all different sizes. Little baby stars, medium stars, big stars. You're not making very many big stars, but those big stars those big stars shine at 1 million to 10 million solar luminosities. And those big stars are all blue, you know, the blue giants, the blue supergiants. And so they tend to dominate the spectra of light anytime you have star formation. So when you see blue in a galaxy, you think, aha, stars are forming. We call it star formation. Or if you see an entire galaxy that's blue, we call it a starburst galaxy. And when stars are not forming, what happens is those blue stars, since they don't live very long, they blow up and you don't see them. And then that region becomes red because of all of the old red stars. So blue means star formation, young stars are forming. Red means no stars are being formed. And what you get is a bunch of old stars sitting around playing canasta and drinking beer. Okay. Central bulge is the concentration. Most of the stars in the galaxy are in the central bulge. This is like downtown. You know, everybody goes downtown. And this halo, as we talked about, is the leftover remnants of when the Milky Way galaxy was formed. Now, this is, I find this confusing, and I have to go over it every time myself. There's two types of stars, and actually there's three, but for the purposes of the course, we're only going to talk about two: population 1 and population 2 stars. The halo contains population 2 stars. The disk contains population 1 stars. One thing to think of is 2 is older than 1. Population 2 stars are older stars. Population 1 stars are younger stars, 1. Halo stars, the population 2 stars, are metal poor. What I mean by that is astronomers use words in ways that are different than normal people. And for astronomers, anything other than hydrogen and helium is called metal. Okay, so that's why astronomers like heavy metal, okay, because they think that everything other than hydrogen and helium is metal, okay? And, you know, if those elements other than hydrogen and helium blow up in supernova, then we call it death metal. So halo stars are old stars. And what I mean by old is that they were born when the universe was young. And if they were born when the universe was young, there wasn't much more other than hydrogen and helium out there. And so their spectra doesn't show very much of things other than hydrogen and helium. So that's why we say halo stars are metal poor. They are old by our standards. They formed when the universe was young, when the universe didn't have a lot of pollutants such as carbon and nitrogen and oxygen and all the things that we know and love that make us up. Okay. And so if they're metal poor, they must be at least 10 billion years old. Population 2 stars are metal poor. That's the halo stars. Population 1 stars are metal rich. These are the young stars. These are stars that are being formed by the guts of the population 2 stars that blew up or spew their planetary nebula stuff into interstellar and intergalactic space. And population 1 stars are formed by these polluted guts of the earlier generation. Our sun is only about 4.6 billion years old. And so it formed from third, fourth, fifth generation stars. It formed from the guts of many, many earlier previous generations of stars. If our star had formed in the early parts, the early ages of our universe, we would not be here because our sun would be metal poor, meaning there wouldn't be enough material around to form planets, rocky planets like us. Okay. And the population 1 stars are typically located in the spiral arms. Okay. Are most of the population 2 stars white dwarfs, or roughly where do they fall? Most of the population 2 stars are going to be red dwarfs. They're going to be main sequence stars that are old. Okay. And there will be a lot of white dwarfs in population 2, but we can't see them. They're just too dim. Okay. But certainly there would be tons and tons of white dwarfs. So what's the size and shape of the Milky Way galaxy? We've talked about the galactic halo, which contains mostly globular clusters formed very early. And this halo around is essentially spherical. The stars are very old and there's no gas and dust in the halo. It's just globular clusters. The galactic disk is where the youngest stars are, and it contains a large amount of gas and dust, and it's where any star formation is happening. Surrounding the galactic center is the galactic bulge, which contains a mix of older and younger stars. And it tends to be kind of white. So not blue, not red, just kind of in between. Does the Milky Way band follow the celestial equator or the ecliptic? Now, this is really confusing, and I apologize for that. So let me boot up another simulation while I go over this. There are 3 coordinate systems. There's the coordinate system defined by the Earth. That coordinate system, so let's bring this up, new share. Okay, here's the planetarium system. And let's options, let's turn off daylight. Okay, so there are the stars. And let's advance that a little bit. Let's go, let's say 300. Okay, now we're facing north, and you can see the stars rotating. And as the stars rotate, you can see the stars are rotating according to the grid. That is the North Star there. You can see that if we bring up the constellations. Oh, let's do the stick figures. Okay, so here is the Big Dipper right there, pointing to the North Star there, and there's the Little Dipper. Okay, there's Cassiopeia over there, and there's the Great Square of Pegasus, and the Orion Nebula is out here someplace. Okay, so this coordinate system is defined by the Earth. It's defined by the Earth's rotation. That pole is the pole of the Earth's rotation. Now there's another coordinate system defined by the plane of the solar system. And that's this green line here, okay? And along the green line are going to be all of the planets and the sun and the moon, because everything along that green line is in a plane that defines the Milky Way galaxy. I'm sorry, the solar system, as we talked about last time. Okay, so Mars is there, the moon is there. So that's another coordinate system. And if we can actually make a grid of that, okay? And that coordinate system is centered in a different place than the rotation. And that's because the Earth's rotation is tilted 23 degrees relative to the plane of the solar system. Unfortunately, there is a third coordinate system. That third coordinate system is the galactic coordinate system. And that coordinate system is the plane of the Milky Way galaxy. And that is defined by this blue line here, which isn't the red, which is our celestial coordinate system. It isn't the green, which is the ecliptic, which is the solar system coordinate system. It is the galactic coordinate system. And so we've got three coordinate systems that you can refer things to. You got the coordinate system of the solar system, the coordinate system of the Earth, and the coordinate system of the Milky Way galaxy. So let's go back to the presentation here. Does the Milky Way galaxy follow the celestial equator or the ecliptic? It doesn't follow either one. Here is the ecliptic plane, and here is the galactic plane. The ecliptic plane is the plane of the solar system, not the Earth. Because remember, the Earth's axis is tilted 23 degrees relative to the ecliptic. So there's the galactic plane there, and it's tilted 60 degrees relative to the ecliptic, okay? And so here we have the ecliptic plane, here we have the galactic equator, and there we have the celestial equator, okay? And so the celestial equator, the Earth is pointed like here relative to that. So three different coordinate systems. And here's a nice video. This video is where we're going from the center of the galaxy on out. And it's going to show you some things that we'll be talking about later on in this lecture. Use parallax to map their distances. Europeans are great people, aren't they? So a question from Roxy, why are young stars in the spiral arms? Young stars are in the spiral arms because it's the kind of the Goldilocks zone. If gas and dust isn't dense enough, you're never going to get it to collapse to form stars. If the gas and dust is really dense, then it's already formed all the stars that it's going to form, and that's going to be true in the for the most part in the galactic bulge in the center of the galaxy, because it's just very dense, and so a lot of star formation has already happened. Whereas in the suburbs where we are, there's a lot of gas and dust. It's not so dense that it's already formed all the stars that it's going to form, but it's dense enough that if you have a passing shock wave or another way of shocking the material and compressing it, then you're going to form a bunch of stars. Okay. So how did the Milky Way galaxy form? There's two hypotheses, and one hypothesis is, as we discussed with the stellar formation, you got a big ball of gas and dust, and it just collapses into this rotating disk in exactly the same way that a solar system forms, as we talked about previously. The other is that it forms by galactic collisions. We know that galaxies collide all the time. And so we call this the bottom-up hypotheses. The current thought, certainly in the last couple of years, is that both of these are active, that you actually have both. And one of the reasons we believe this is that we recently have evidence of at least 40 previous collisions with other galaxies in the Milky Way galaxy. And that evidence are where you have these swaths of stars that seem to be related to each other, but are not related to anything that's currently in the Milky Way galaxy. And we believe that these are the remnants of collisions with other galaxies. And in future lectures, we will show you simulations of those galactic collisions. And in fact, if you happen to be around, in 4 billion years, the Andromeda galaxy is going to slam into our galaxy. And so that'll be a very spectacular collision. So mark your calendars, a little over 4 billion years. I believe it'll be on a Saturday. Okay. And we see lots of evidence for these spiral streams with the galactic collisions that we can observe. Okay. And here are some of these streams that we have been able to detect around the Milky Way galaxy. And we've detected these streams around a lot of other galaxies. So a galaxy that appears to be populated by mostly red stars is likely, let me bring up a poll. A, never had blue stars. B, had blue stars, but are not present, that are not present anymore, but were there once long ago. C, has been around long enough for blue stars to evolve into red main sequence stars. D, never contained enough gas to have blue stars. E, has blue stars that are being blocked by dust. Okay. We got a lot of B, but mostly C. And here's the thing. Blue stars do not evolve into red stars. Remember, once a star winds up on the main sequence, it spends 90% of the time on the main sequence. Once it reaches the main sequence, it doesn't move. So a blue star, it hits the main sequence, it stays there, it stays blue. And the next thing that happens is it explodes in a supernova. And so blue stars will never evolve into red stars. Okay. So the correct answer is B. How do spiral arms form? We don't know. So you would think that the spiral arms form because it just kind of winds up as it rotates, because the center part will rotate faster than the outer part. The problem is that can't be true. It can't be true because if it was true, in a very short amount of time, just a few 100 million years, the spiral galaxy would have wound up so much that the spiral arms would have been all on top of each other. And we know that's not true. So something else is creating the spiral arms. And the thing that we think is causing the spiral arms is what's called density waves. That we have these waves of star formation, of shocks formed by various supernova. And those waves of shock formation then propagate out as a series of waves around the spiral galaxy. One way to think of it is like a traffic jam. A traffic jam is an increase in density in the traffic, even though it's not an increase in density in any particular car. Cars come in and out of that traffic jam all the time. It's the traffic jam itself that stays in the same place. So it's not like the same stars stay in these particular arms. The stars pass through the arms. It's just a bunching up of that. Anyway, that's one theory. Computer simulations kind of show this feature. So we think it's okay. But again, we don't have a smoking gun that this is the absolutely correct theory. So what is the mass of the Milky Way galaxy? One way you calculate the mass is how fast stuff rotates around. So if I throw a ball and it goes into orbit around the Earth, it'll take about 93 minutes to orbit the Earth, which is about the time that the ISS takes to go around. If the Earth was twice as massive, then it would take you'd have to orbit much faster. And so that orbit would be a lot faster. And so by measuring how fast things spin around, you can measure the mass of the thing it's spinning around. And so when we see planets orbiting suns, we can tell you exactly what the mass of that star is because we can just calculate how fast the object is orbiting around. And so we do that. Now, like I said, most of the stars we observe is in this galactic bulge. It's in the center. There's very few stars, relatively speaking. There's 100 billion up to 400 billion stars. The estimates are kind of all over the place, but it's hundreds of billions of stars in the Milky Way galaxy, and the vast majority of those are in the bulge. And so what you would expect is that um, stars close to the bulge would go around very quickly, as Mercury goes around very quickly in our solar system. And out here on the edge of the disk, stars would go around very slowly, as Pluto goes around very slowly. Mercury goes around the sun in 88 days. Pluto goes around the sun in about 250 years, okay? And so we'd expect exactly the same thing in the Milky Way galaxy. Close up, things spin fast. Far away, things spin slowly, okay? And this dashed blue line is exactly what we'd have expected, because this dashed blue line is exactly the rotation curve for the solar system. Things close to the big thing that's at the outer edges spin fast, and then things at the outer edges of the disk would spin really slowly, okay? And this assumes that all of the mass is in the galactic center. And since our observations show the vast majority of stars are in the galactic center, that's a pretty good approximation. When we map it, we don't get that. We get the red line, okay? So the red line continues out to where stars and the farthest reaches of the Milky Way galaxy are still spinning very, very fast. This makes no sense. What this says is our assumption that all of the mass is concentrated in the galactic center must be wrong. There must be other mass, okay? And we'll be coming back to this over and over in this course because this was a critical discovery. This discovery was first noticed in the 1930s. I think Vera Rubin really pinned this down in the 1970s. And now we have hard evidence for this with virtually all galaxies, that the galactic rotation curves don't make any sense. They don't match up what we see with the stars. And this was our first evidence that we knew nothing. You knew nothing, Jon Snow, about the universe. And we've known since 1999 that we know nothing, Jon Snow, about the universe. And this was the first evidence for that. So more than twice the mass of the galaxy has to be outside the galaxy that we see. In other words, more than twice the mass of the galaxy has to be stuff we cannot see. In fact, we now think it's about 10 times more. And we call that unseen mass that we cannot observe dark matter, and we'll be coming back to that in future lectures. In addition to this dark matter mystery, we also know that there must be a black hole at the center of the Milky Way galaxy, not because we can see it with visible light, but because we can see it with infrared, X-rays, and radio waves. But infrared and radio shows that there are stars at the center of the galaxy that are orbiting something very, very quickly. They're orbiting so quickly that whatever they're orbiting must have a mass of 4 million suns. No star can have a mass of 4 million suns. It can't. The laws of physics prohibit a star that big. The laws of physics prohibit stars greater than about 100 solar masses. So we know that it must be a black hole, which is no big surprise because we've observed black holes at the center of basically every galaxy that we've ever looked at. So there is a black hole at the center of our galaxy. We have evidence for that not only with the stars orbiting very quickly, but we also have evidence because we've mapped the extremely strong magnetic fields close to this, whatever this is, assumingly a black hole. And we've also been able to have observations of an accretion disk, as you would expect around a black hole. And there's very, very strong X-ray emission from this, again, as you would expect from a black hole that's eating stars for breakfast and lunch and dinner. And so the evidence is basically overwhelming for a supermassive black hole at the center of our galaxy. The location of that is known as a Sagittarius A star for historical reasons. So if you say Sag A star to an astronomer, they know what you're talking about. What they'll assume you're talking about is the supermassive black hole at the center of our galaxy.
Hiding behind the constellations Sagittarius and Scorpius is the center of our own Milky Way galaxy, over 25,000 light-years away. This patch of sky is mostly dark and visible light, shrouded by dust clouds that lie between us and the galactic center. But the infrared vision of NASA's Spitzer Space Telescope sees through the dust, showing us this strange and tumultuous region. The image spans about 5 degrees of sky, which is about half the width of your outstretched palm, but encompasses over 2,000 light-years across our galaxy's core. Infrared light at 3.6 microns, which is mostly from stars, appears blue in the Spitzer image. Dust clouds glowing at 8 and 24 microns are rendered in green and red. The stars dramatically increase in numbers towards the center, swirling around a supermassive black hole astronomers think lies at the heart of it all.
And so here is observations over time of these stars that are close to the center of whatever is there. And that little red X is the center of the mass of whatever they're orbiting. And look at how fast these stars are going. So we know that there is something really, really massive that we can't see in visible light at that X. And last year, we thought that we were going to see one of these stars getting swallowed. Unfortunately, it didn't. But we believe the next pass it will get swallowed. And here's another mapping of that. And here you can see that this is in years. And so you can see approximately how fast this is really going. I think that was the one we thought was going to get swallowed. And here's a... And we'll finish with another video. Then I have a bunch of quizzes for you. Not quizzes, polling questions. You can recognize the Orion Nebula constellation here. Here's the belt of Orion. There's the sword of Orion, and there's the Orion Nebula, which we're about to pass through. And now we're rising above the plane of the Milky Way galaxy. – 100,000 light years across. Now, in future lectures, we'll talk about these other galaxies, the local group of galaxies, the Virgo cluster, the supercluster, and then the cluster of all of the galaxies in the, there's the Andromeda galaxy. So I said that our Milky Way galaxy consists of several 100 billion stars. The observable universe, the universe we can observe, contains several 100 billion galaxies. The universe is a big, 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 big place. And that's just the observable universe. We don't know what goes beyond there. So Thomas asked, about what year do you think that another planet will get swallowed by the supermassive black hole center of the galaxy? Unfortunately, I don't know. I'll have to look that up. Thanks for asking. Why don't I believe in aliens? Yes, that's correct, Matthew. The Fermi paradox. Our galaxy has been around for 12 billion years. And in those 12 billion years, if there are millions of technological civilizations, at least one of them would have colonized the galaxy, because it only takes a few million years to colonize the entire galaxy. And we know for a fact none has, because we don't have any evidence for a galactic civilization. So that implies that advanced intelligence is very, very rare. In fact, I've got an entire course that I just taught at Duke about that, where we talk about the Great Filter and the Kardashev scale and rare earth and things like that. Anyway, let's wrap up with some polling questions. So, relaunch. Yeah, so Josh, I do think that we will be the first to be a galactic civilization if we can get there before we kill ourselves first. So our sun is located in the Milky Way galaxy, about 30 kiloparsecs from the center of the halo, 30,000 light years from the center of the globular cluster C at the edge of the galactic disk in the plane, about halfway from the center in the spiral arms, E in the bulge near the Orion arm. Read this very carefully. Okay, so most of you are wrong. Okay, and read this very carefully. 30,000 light years, it's not too far off from the center in a globular cluster. Where are globular clusters? Let's try that again. Same question. And that's exactly correct. About halfway from the center in the spiral arms. Okay. Halfway from the center in the spiral arms, about 8 kiloparsecs, which would be about 24,000 light years. Okay. Plus or minus. Some people say 30,000 light years. So in that ballpark. And again, we think that the radius of the Milky Way galaxy is about 40 to 50,000 light years. So that would be about 15 kiloparsecs. What observations allow us to estimate the galaxy's mass? A, the sun's mass and velocity in orbit around the galactic center. B, the rotation of the bulge and disk components. C, the sun's age and age of globular clusters. D, the motions of spiral arms, the mass of the central black hole. E, the sun's orbital period and distance from the center. Wow. There's really no consensus here. Your answers are all over the map. Now, remember, if I'm trying to map the mass of a sun, and what I do is I look at the exoplanets that are orbiting that sun, and I see what is their orbital period and how far away are they from the sun. And based on those, I can calculate what the mass of the sun is. So let's try this again. Yeah, so John, the great filter says that if there's aliens that have been killed, that implies that there's that's good news, because that would imply that there is a filter that we have already passed through. But if there's aliens that are approximately our level of technological development, and we know that no civilization had ever achieved galactic status, that means that the great filter is ahead of us. Anyway, that's a different course. So that's the correct answer. It's the sun's orbital period and distance from the center. A is wrong. Certainly the velocity in orbit is correct, but the sun's mass is irrelevant for this. So that's why A is wrong. The rotation of the bulge and disk components, that's kind of a nonsensical answer. The age and age, again, that's nonsensical. That this doesn't have anything to do with it. D, a lot of you chose D. The motion of spiral arms and the mass of the central black hole. Yeah, so this is what we're trying to calculate, not what we're trying to observe. So let's go to the next question. What's the approximate mass of the Milky Way galaxy? And that's correct. It's about 200 to 300 billion solar masses. And I've seen estimates for the number of stars as high as 1 trillion, just because most stars are not that heavy. Most stars are these red dwarfs. But I've also seen estimates as low as 400 billion. So, but still, hey, 400 billion is still a lot of stars. And it's especially a lot of stars when you think that when you go out to the night sky, and even on a clear night, you can see at most 3,000 stars. And there's 2 to 400 billion of those puppies out there that you can't see. Okay. And let's stop it there. And I'll open it up for any questions. Any questions? Thank you all. Thanks. Have a great weekend, everybody. And congratulations to joining the last section of this course when we talk about stars, galaxies, and really cosmic things. I hope this is the most cosmic class you've ever had. If our solar system was float off out of our galaxy, would we still survive? So Bennett, absolutely yes. Now, if you asked a different question, if our solar system drifted into the center of our galaxy, yeah, that would be a bad day. The radiation level there is so high that we wouldn't survive. Is this the last lecture? No. This is not the last lecture. This is lecture 17 of 24. We've got 2 lectures next week, and then the following week I got 1 lecture and then exam number 3. Do you think wormholes are possible? Einstein's equations predicted allow wormholes, but the current theory thinks that we need a vast amounts of negative energy, which we don't think exists, or negative matter, to keep a wormhole open. So I think it's a mathematical possibility. I don't think it's a practical possibility. Look up the Great Filter. Wiki has a whole bunch of things to say about it. Do supermassive black holes collapse to a near singularity like most black holes do? And if they do, does that mean there's no theoretical limit to how dense something can be? Matthew, if you knew the answer to that, you'd win a Nobel Prize. We just don't know. We don't know. The reason we don't know is that the equations of quantum mechanics and general relativity both break down when you reach those densities. They just don't work anymore. They make nonsensical answers. And so we know for a fact that neither quantum mechanics nor general relativity is a complete description of reality, because they don't work with matter inside a black hole. What's more practical, life on Earth or wormholes? Life on Earth. What is the most plausible theory for the end of the universe in your opinion? Big Rip or another Big Bang, maybe? So Marcin, I would highly recommend The End of Everything, a book by Katie Mack, who co-teaches this course at NC State. It's a fabulous book. The End of Everything by Katie Mack. Actually, the title is called The End of Everything, Astrophysically Speaking. Does the last question about the mass of the Milky Way include dark matter? Yes, it does. That's a good question, Andrew. And we'll talk more about that in a future lecture. Other questions? Okay, if there's no further questions, thank you very much, and I will see you all on Tuesday.